All right, so that's chapter 10 notes. It's our unit 3. So when you look online, the folder and everything, it'll be unit 3. But is it? It's this one and one more. And that's the last two. We have this one and linear regression. Linear regression should be a throwback to Algebra 2. A lot of stuff we've already done before. This is new. We did not do chi-squared in Algebra 2. So, and it is chi-squared, not chi-squared or chi-squared. It is chi, that's how it's pronounced, just so you know. Okay. So, in previous chapters, we've been doing inference for categorical counting data, but only for variables with 2 categories, success or failure. In this section, we will be considering univariate categorical variables with 2 or more categories, such as ethnic group or college major or types of cereal or types of candy or whatever, types of colors, that kind of thing. So, example 1. At one time, the intended distribution of colors in a bag of regular M&Ms was 10% blue, 10% brown, 10% green, 10% orange, 20% red, yellow, and purple. So that's what, theoretically, if you open up a bag, that's what should be in there. Doesn't mean it's going to be in there exactly, but that's the theoretical what they expected to have in there. So, suppose we open a random bag, sample bag, and observe the count below. Does the data indicate that the stated distribution has changed? So, we open up a bag, there were 250 pieces, 250 M&Ms in the bag. There were 28 blue, 21 brown, and you can read the rest, so forth. Okay. That's observed count. We're going to talk about the expected count. What did we expect to be in there? Okay, well, it says, below the sample size is an important consideration. We consider the expected counts in each category. So, we expected 10% for blue to orange. This was supposed to be 10% of the total. And this was supposed to be 20% each of the total, 250. So, quite simply, if we take 250 and multiply by 0.10 on the calculator, or just simply move the decimal left, we get 25 for all of these. So, blue, brown, green, and orange, we expect 25 of each color. 20% is double that of 10%, so quite simply 50, 50, and 50. Okay, that's what we expect. So if we open up a bag with 250 pieces, that's what we should get. So blue was a little bit lower, brown a little bit higher, green more, well, a little more higher, orange a little low, red a little low, yellow quite a few more, and purple not as many as we expected. That would be the breakdown we would expect. Okay, so how likely is it to get differences like these due to just sampling variability? We need to first figure out a way to measure how different the observed counts are from the expected counts. And that's what leads us into chi-squared. Okay, so this is the actual way we calculate chi-squared. And this is a little tedious. I'll tell you, we're going to use it on the calculator, but it's a little tedious. And if you notice, it looks like a normal x squared, but it's actually a little kind of a curvy line and a straight line. So that's how you do it. A little curvy line and a straight line. That is chi-squared. All right? This right here means summation. That funky looking E is summation. We're going to add a bunch of things. What are we going to add? Well, we're going to do some fractions. We're going to take the observed count minus the expected count. So how many we saw minus how many we expected. We're going to square that number and divide by the expected count. And that's going to be a fraction. And we're going to add every fraction up. It's easy. It's just time consuming. Okay, so chi-squared measures the total relative differences between the observed and expected counts. Therefore, as chi-squared gets bigger, we have more evidence that the observed distribution differs from the expected distribution. Okay? So the bigger chi-squared, the more difference there is. So we're just copying these numbers here to see them again. 25, and then 50, 50, and 50. All right? So here's how we do the math now. Find the test statistic and the p-value. So we write our little curvy line, we write a straight line, and here we go. So using our chart, we're going to go color by color. So blue, our observed minus expected squared divided by expected. That's one fraction. Plus 21 minus 25 squared divided by 25, the expected. I want to keep doing that. All right, so there's my 7 fractions. We have 7 colors, 7 fractions. Every category will be a fraction for. So what you're doing now is you're going to take our calculator, and we need to practice this. So we'll get started and hit pause in the video. So, we're going to turn it on. Maybe? There we go. Whatever. All right, so we're going to turn it on. We're going to hit alpha y equals. Enter. Now, you have a choice. You can enter in, parentheses 28 minus 25, parentheses squared, and then come down here and put 25. All right? Now, when you want to go to the next fraction, you got to hit this right arrow and then put your plus. Then we're going to hit alpha solve again. Alpha y equals again. Now, you have a choice. If you don't want to type in 21 minus 25, because you can do the math in your head, you can type in, know that it's parentheses, -4, parentheses, squared, whoopsie, squared. Nope, don't want that either. Nope. Go over there, delete. There we go. I'm just going to be sure. Okay. Why is this not working? Squared. There we go. And then down here, just put your 25. Now I may get an error because I'm not sure what's going to happen with these boxes up here. Okay. All right. Sorry about that. All right. Plus, now our next one. Also, if you want to save time, 19 minus 25. That's -6. If you don't want to put -6 in parentheses squared, and you just go, I know that that's 36, you can also just put 36 over 25. It's up to you. Whatever you want to do in your head, save time, go ahead. All right? So the next one is 29 minus 25. So I know that's 4. 4 squared is 16. So I'm just going to hit plus alpha y equals 16 over 25. Right arrow. Hit plus. 55 minus 5. I know that's going to be 5 squared, 25. So alpha y equals 25 over 50. Right arrow. Our next one is this one. Okay, 39 minus 50. So 39 minus 50 is going to be -11. Squared is 121. So plus alpha y equals 121 over 50. Then plus, last but not least, 59 minus 50 is going to be 9. 9 squared is 81. So 81 over, or not, 81 over 50. And then we're going to hit enter and hope. Yes, that is right. So I got 381 over 50. Hopefully you did too. Now, we want to turn this into a decimal. So it's very simple to do that. You hit the math key. See how it says number 2 decimal? 7.62 equals 7.62. So your answer was in a fraction form, like so, 381.50. You hit the math key, and you just hit number 2. Turn it into a decimal. Hit enter. 7.62. That's how you turn decimals to fractions, fractions to decimals. All right. Now, degrees of freedom, like it says right here, is the number of categories minus 1. So that's 7 minus 1, which is 6. Now, the p-value is going to be similar to what we did last unit. We're still going to do second bars. I'm going to write the steps down here so you won't copy it down. So we're going to hit second. It's a big second. Second bars. Okay, so the second key and the bars key. And then we're going to choose number 8, which looks like this. X squared CDF. Okay, so show it on the calculator. So you hit second bars. And it's not on here, but it's number 8. So you just hit 8. This is going to look familiar. Okay? But think about it. Since we're always squaring our number, our chi-squared is always going to be a positive number. So our chi-squared is always going to be our lower, 7.62. Our upper, we always put in 999. Our degrees of freedom, we just said was 6. We hit enter, enter, again enter, and there it is, 0.2673, because the 8 rounds the 2 up. So p-value is 0.2673. So we got our chi-squared and we got our p-value right there. Okay, example 2. Now notice, we only have one row of numbers here. It says to see if birthday is related to whether a player makes in the NHL, a random sample of 80 players from a recent season was selected and their birthday is recorded. The table summarizes the data on birthdays for these 80 players. This is calculate the expected counts for a test of the null hypothesis that the proportion of all players born each quarter is the same for all quarters. Well, this is our observed. We're going to have expected. If there's 80 people and you want the same number in all 4 quarters, you're going to take 80 divided by 4 and get 20 in each category. All right? Now we're just going to do the same thing. So, our chi-squared, funky curve, straight line, equals. Our first number was 32 minus 20 squared over 20 plus, this one's nice, there were 20 in this quarter, minus 20 squared over 20 plus 16 in this quarter, minus 20 over 20. And finally, the fourth one, 12 minus 20 over 20. One of those fractions goes away. Which one? 20 minus 20 is 0. Squared is 0. Divided by 20 is 0. So we actually only have to do 3 of these. So we take our handy-dandy calculator. We hit alpha y equals. Enter. And we only have a few to do. So 32 minus 20. Again, you can type this in if you want. All you can do in your head. 32 minus 20 is 12. 12 squared is 144 over 20. Right arrow, plus. You need to practice this. Alpha y equals ND. 16 minus 20 is negative 4. But when we square that, that's 16. Always getting a positive number over 20. And our last one, our third one, is 12 minus 20, which is negative 8. But when we square that, we get positive 64. Whoopsie, I screwed that up big time. Alpha y equals enter. 64, and the expected value was 20. We hit enter a few times, and we get 56 over 5. But we want a decimal, so again, what do? We hit the math key. We just hit number 2 and enter, and we get 11.2. Easy enough. That is our chi-squared term. Notice that's bigger than our last one, which was 7.62. To get our p-value, we just take our calculator. We hit second bars. Please practice this. Get number 8. Our lower value is always the chi-squared. We don't even have to change the 999. We do need the degrees of freedom, which I forgot to write down, so let's go back and do that. Degrees of freedom, there's 4 quarters minus 1 equals 3. So we can leave the 999 and just change this to a 3, hit enter a few times, and there we go. Now careful, the 6 rounds up because of that 9. So our p-value is 0.0107. That's it. Notice, the homework is 5 through 12 all. But 5 goes with 9, 6 goes with 10, 7 goes with 11, 8 goes with 12. So we'll talk about that. So you might want to get your piece of paper up, and I'm going to do some of these with you. We're going to start at number 5. This is online. Number 5. Notice how it says refer to exercise 1. So number 1 is down here to refer to. Next page. There's 1. So it says, are you nuts? A company claims that each batch of its deluxe mixed nuts contains 52% cashews, 27% almonds, 13 macadamia, and 8% Brazilian nuts. Statistics claim a quality control inspector takes a random sample of 150 nuts from the latest batch. State appropriate hypothesis, blah, blah, blah. So let's go to number 5 and see what it says. Number 5 actually has the count laid out for you. Okay? So there's the layout for you. 83, 29, 20, 18, and 150. So you might want to copy this over to your... So, number 5. Here we go. We have our observed and expected. And we have 83. You can put the labels up there. I'm just putting the numbers. You should put the label, the nuts above. 20 and 18 for a grand total of 150. So I know this was Brazilian. I think this was macadamian. I don't know what the other two were. Just put it 29, 20, 18, and 50 is the total. Now, if you look at it, it says in the number 1, okay, it says 52% cashews, 27 almond, 13%, and 8%. So what we're going to do is we're going to take these and turn them into decimals, 0.52, 0.27, 0.13, and 0.08. Come back to our macadamia. Cashews and almonds. There we go. So cashews, almonds. All right, so what we're going to do is we're going to take 0.52 times 150. And that's going to give us 78. Because that's what they expect. They expect 52%, which is 78. And then we're going to take 0.27 of 150. And that's going to give us 40.5. Now, obviously, we can't have half of a nut in there, but this is just the mathematical expected number. For macadamia, they expect 13%. So 0.13 times 150. Sorry, the 150s are looking like 180s, but that's the board. And that gives us 19.5. Again, not going to have half of a nut. Make it 70, you could have one break off. And last but not least, Brazilian, 0.08 times 150 would be 12 Brazilian nuts in the mixed nuts. Okay? Now, we're just doing the same thing. So notice how 5, you had to go refer back to 1 to get the percentages to find the expected values. But now from there, we're just going to do the same math. 83, so chi squared equals 83 minus 78 squared over 78. Plus 29 minus 40.5, yes, go with the decimal, do not round, over 40.5. That's squared. Plus 20 minus 19.5 squared over 19.5. And finally, 18 minus 12 squared over 12. Okay, so I got 6.599 or 6.6 as a decimal after you convert the fraction. That's what you should have got. All right. Can help you out with 6 also. If you'll have some trouble with this. Wrong way. 6. All right. Here are the results of the sample of 200 spins. Calculate the expected counts for a test of all of the null hypothesis in exercise 2. So we got to go look at number 2. So for number 2, it says casinos are required to verify that their games operate as advertised. American roulette wheels have 38 slots, 18 red, 18 black, and 2 green. The managers of a casino record data from a random sample of 200 spins of one of their American roulette wheels. State appropriate hypotheses for performing a test of this roulette wheel. Okay? So for number 6. We have our expected, we have our observed. We have red, black, green, and total. So again, 85, 99, and 16. Okay? So 85, 99, and 16 for a total of 200. Now, from what we got in the problem number 2, it said there's 38 pieces on the roulette thing that the ball can fall into. They want 18, there's 18 red out of 38. Okay, so this requires an extra step. So the last one, we had to calculate the decimal. This one, we have to figure out what the fraction is, then calculate the decimal. So there's an extra step. So 18 out over 38 is 0.47. Well, if there's 200, then you take 0.47 times 200, and that gives us 94.7. Again, the decimal is the mathematical expected value. Now, since there's 18 black, it's going to be the exact same thing. So we can just copy this over. We know it's going to be the same number. And for green, it tells us that there's 2 out of 38, which is 0.0526. So if we take 0.0526 times 200, that gives us 10.5. That may not exactly add up to 500, 200 because we have decimals, but it's going to be pretty darn close. And it's not going to do for number 6. But it was kind of complicated for that extra step. And real quick, I'm going to give you 2 little hints on numbers 3 and 4. Like I said, it's going to be really close. I want to give you hints on 3 and 4. It referred to 3 and 4. So on 3, it says the color of the original Skittles uniformly distributed. Okay? There's 4 bags. Investigator J and Doden bought 4 bags of original Skittles and count how many there were. And then number 4, you're talking about Kellogg's Fruit Loops, and there are 6 colors. Okay? So it says in this one there are green, red, purple, yellow, and orange Skittles. So 1, 2, 3, 4, 5 colors. Right? And there's how many total? 233 total. Okay? So, a little hint for number 7. Again, remember 3 refers to 7, and this refers to 8. Those two are together. Those two are together. So 3, 7, there's 233 divided by 5 colors for the Skittles. And for the Fruit Loops, if you look at the book, it says 120, and there were 6 there, so that's for the Fruit Loops. So that's just a little hint for you.